In this problem, we will develop the formula for the confidence interval for the population variance. You'll see in a minute that the formula for the confidence interval for a population variance is different than the confidence intervals that we're typically used to seeing for the population mean or the population proportion. And the reason is because the confidence interval for sigma squared, the population variance, is based on the sampling distribution of not sigma squared, but it's based on the sampling distribution of the quantity n minus 1, where n is the sample size that you use to estimate the population variance, times s squared, which is the sample variance, divided by sigma squared. That value has a chi-squared distribution with n minus 1 degrees of freedom. Before going any further, let's review the confidence intervals and the sampling distribution for the sample statistic used to estimate the population parameter. When we were estimating the population parameter mu and constructing the confidence interval, we used x bar as our sample statistic as our estimate for mu, and the sampling distribution of x bar was normally distributed. If we were trying to estimate the population proportion, we used the sample proportion, and its sampling distribution was also normal. When we were estimating mu1 minus mu2, the difference of population means for two different populations, we used x1 bar minus x2 bar as our estimate, and its sampling distribution was normal. Estimating the difference of population proportions in two populations, our estimate was p1 hat minus p2 hat, and its sampling distribution was normal. Recall our recipe for a confidence interval for any of these confidence intervals. It was always the estimate of the parameter plus or minus a critical value times the standard error of our estimate. Our confidence intervals were always symmetric, and the center of the confidence interval was always the estimate of the parameter. Why was it symmetric around the estimate of our parameter? It was symmetric because the sampling distribution for our estimates was normally distributed, and the normal distribution is a symmetric distribution. If you look at our current problem, the sampling distribution is based on a chi-squared random variable or chi-squared distribution, which is right skewed and it's not symmetric. So we're going to find that our critical values are not just opposites of each other. If we rearrange this, multiplying both sides by chi-squared, or multiplying both sides by sigma squared and dividing both sides by chi-squared, we have the following: n minus 1, the quantity, times s squared divided by a chi-squared critical value is sigma squared. And this is the form that our confidence interval will take. Our confidence interval for sigma squared, the population variance, the lower bound is given by the quantity n minus 1 times the sample variance divided by a chi-squared critical value. The upper bound is given by n minus 1 times s squared divided by a different chi-squared critical value. Again, these two values are not just opposites of each other because the sampling distribution that our confidence interval is based on is not a symmetric distribution. Let's look at how to find these critical values in a confidence interval. Here we have a chi-squared distribution with n minus 1 degrees of freedom. It is right skewed. If we are looking at a C confidence interval, we want to have C, the area of C, between our two critical values, and we want to have equal areas above the upper critical value as below the lower critical value. So if there is area C in the middle, that leaves 1 minus C for the two tails, and we want equal amounts in the two tails. So in the upper tail, we should have 1 minus C over 2. That should be the area of the upper tail, and that's also the area of the lower tail. 1 minus C over 2. C is between the two critical values, and above the upper and below the lower is 1 minus C over 2. Let's actually calculate the critical values for a 95% confidence interval for sigma squared based on a sample of 21. If our sample size is 21, then the sampling distribution that we want is a chi-squared distribution with 20 degrees of freedom. If we are calculating a 95% confidence interval, we want 95% of the area to be between the two critical values. How much does that leave for each tail? For the two tails together, it leaves 5%. We want equal amounts in each tail, so we want 2.5% in the upper tail, and we want 2.5% in the lower tail. Now we need to find the critical values associated with that. For this, we go to a chi-squared distribution table. We need to be using the degree of freedom row of 20. The chi-squared upper critical value has 2.5% of the area to the right of the critical value. So for 20 degrees of freedom, we want the critical value that has 2.5% of the area above the critical value. That critical value is 34.17. To find the lower critical value, how much area is to the right of the lower critical value? It is 97.5%. So degrees of freedom 20, 97.5 area to the right has a critical value of 9.59. So our upper critical value for a 95% confidence interval based on a sample of size 21 will be 34.17, and the lower critical value will be 9.59. And we see that our confidence interval will be 20 times the sample variance, whatever that turns out to be, divided by 34.17. Our upper bound will be 20 times the sample variance divided by 9.59. Before leaving this problem, we should also talk about the confidence interval for sigma instead of the confidence interval for sigma squared. Usually it's easier to think in standard deviation units as opposed to variance units. All we need to do to get the confidence interval for sigma as opposed to sigma squared is to take the square root of our lower bound and the square root of our upper bound. So we see that the confidence interval, the lower bound for the confidence interval for sigma is the quantity n minus 1 times s squared divided by the upper critical value. The upper bound is the square root of n minus 1 times the sample variance divided by the lower critical value. So in either case, you can construct the confidence interval for the population variance or the population standard deviation.